Hello all. In the last class we completed drawing the resonating structures, right? Let us continue some more examples. Okay, right. Drawing resonating structures. Drawing resonating structures. Continuation. Let us draw the resonating structure for this. Okay. Oxygen contains 2 lone pairs. Remember, nitrogen contains 1 lone pair. Halogens contain 3 lone pairs on them. Right? Okay. Remember one point. Throughout organic chemistry, negative charge is considered as a bond. Lone pair is considered as a bond. Negative charge also considered as a bond. Negative charge is considered as a bond. Lone pair is considered as a bond. Right? Now, here lone pair is present now. Lone pair means we are considering it as a bond. Lone pair as a bond. So, shift this lone pair as a bond in between these two. See the arrows. While drawing the resonating structures, representation of arrows are very, very important. Okay. This lone pair is shifting as a bond in between these two. Okay, then what we will get? Here we will get double bond. Okay, because this lone pair is converting as a bond. Next, I am writing positive charge on the oxygen. Why oxygen is getting positive charge? Because oxygen is losing its electrons. Oxygen is giving its electrons, donating its electrons. That's why it will get positive charge. Clear? Right. Next. Applications of resonance effect. Applications of resonance effect. See, before starting applications of resonance effect, let us write what are plus M and what are minus M groups. I already given in the last video. Okay. Again, I am writing some plus M groups and minus M groups. O minus. Sorry, here we have to keep heading plus M. O minus is a plus M group. NH2, NHR, NR2, OH, OR, ester. I given already in the last video. Amide also. All these are plus M groups. Plus M. Okay, very, very important point. Every plus M group also has minus I effect. Every plus M group also has minus I effect. See, sometimes we'll get the question also, which of the following has both plus M and minus I effect? See, O minus is having plus M effect and minus I effect. Means O minus can donate electrons and it withdraw electrons also. Similarly, NH2 is having plus M effect and minus I effect also, like that. Remember, okay? Right. Minus M groups. I already given plus M minus M groups in the last class. Okay. NO2, cyanide, aldehyde, ketone, carboxylic acid. Okay. Even ester also, but the linkage is different. Here ester is linked through carbonyl carbon. Okay. Amide also. These are minus M groups. And very, very important point, every minus M group has minus I effect also. Minus I effect also. What is the effect shown by NO2? Minus M and minus I. What is the effect shown by cyanide? Minus M and minus I. Every minus M group also has minus I effect. This is very, very important. Okay. Remember this. And here I wanted to explain one important point about halogen. What is the effect of halogen? Halogen. See, halogen is considered as a strong minus I group. Minus I effect it is having. And it is also having plus M effect also. Why? See. X. Fluorine, chlorine, bromine, iodine. every halogen is having plus M effect as well as minus I effect, remember. If I ask you what is the effect shown by chlorine, plus M effect and minus I effect, okay, right. Let us see one table which gives more clarity about the concept of plus M minus I, okay, right. Group or atom, plus M minus M plus I and minus I, minus. OH comes under which category? OH comes under which category? OH is a plus M group. Every plus M group also has minus I effect, na? So tick minus I, like that. Aldehyde. What is the effect shown by aldehyde? Tell me. Aldehyde is a minus M group, minus M and minus I, minus M and minus I. O minus is plus M group. Plus M, but it is considered as a plus I, not minus I. Okay, exceptional case. In generalization, I given there only. Okay, here I given like this only. Means O minus is also having minus I, but exceptional case. Okay, this concept is for only these. Means plus M minus I. Okay, except O minus, remaining all are having minus I. Remember that point. Okay, very important. Oxygen is having plus I effect. Okay, only for oxygen plus I effect. Clear? Right. Next, what about chlorine? Chlorine plus M minus I. Halogen. Just now I explained about halogens. Halogens are having plus M and minus I. So what is final conclusion? Which group is having plus M effect and minus I effect? Halogen and O minus. Right? Okay. Coming to the applications. Okay. First, applications of resonance effect. Resonance effect are also called as mesomeric effect. Resonance effect or mesomeric effect. Okay. First application, stability of carbocations. Stability of carbocations. We know carbocations are stabilized by which groups in inductive effect? Carbocations are stabilized by minus I groups only, na? Right? Carbocations will be stabilized by minus I groups. Sorry, plus I groups, carbocations. Here also carbocations are stabilized by plus M groups. Carbocations are stabilized by plus M groups. So I am writing that plus M groups increase stability. Plus M groups increase stability of carbocations. C plus means carbocation. Minus M groups, electron withdrawing groups, decrease stability of C plus. C plus stands for carbocations. Okay, right. When plus M effect is present in a carbocation, that is more stable carbocation. When minus M effect is present in a carbocation, that is unstable carbocation. For example, once let us revise structural requirement for resonance and we will start. What are the structural requirements for resonance? If any unsaturated center is connected to an atom with positive, then resonance is present. Atom with negative, resonance is present. Lone pair, resonance is present. Single electron, resonance is present. Double bond, resonance is present, right? And second requirement. If any atom connected directly to carbocation with lone pair, there also resonance is present, right? Okay. These are the structural requirements for resonance. Let us start the applications and examples. First example. A very simple example. See, while predicting the stability of carbocation, first we have to check whether resonance is present or not. Okay, if resonance is present means positive resonance plus some effect is present, that carbocation is more stable carbocation. Clear? In option A, resonance is present or not? Yes, in option A, resonance is present. Why? Oxygen is having lone pair and oxygen is connected directly to carbocation, so electron transfer will takes place and this carbocation will get 2 electrons and get stability. So write within the bracket resonance is present. Reso means resonance is present. So first one will be more stable carbocation. Okay, so we can eliminate first option. First one is more stable, no doubt. Coming to B and C. In B, is there any resonance? No. In C, is there any resonance? No. But in C, minus I group is present. Minus I group is present. Fluorine is a minus I. Na? What minus I groups will do? They decrease the stability of carbocations, right? Instead of increasing the stability, they decrease the stability of carbocations. So between B and C, which is stable carbocation, B is stable carbocation. Why? B is not having minus I group, right? Okay. So what is overall stability? A greater than, B greater than C. C is least stable due to presence of minus I, right? Let us go with the important example, very important example. Example 2. Here oxygen atom, right? Which is stable carbocation. Same procedure. First we have to check for resonance, where resonance is present. I given already about structural requirements or structural conditions. Which structure is satisfying the condition for resonance? In option A, or first structure, right? Why? Because oxygen is having lone pair which is connected directly to the positive charge, means carbocation. So resonance is present, electron transfer takes place, that will be more stable, right? So identifying the presence of resonance is very, very important. Clear? Right, first one is more stable because resonance is present, positive and oxygen with lone pair are adjacent to each other, right? Next, see this one, option B. In option B, resonance is not present. Why? Because oxygen is not connected adjacent or not present in adjacent position. In between carbocation and oxygen, one CH2 is there. So here resonance is not present. Remember, when oxygen is directly connected to carbocation like this, okay, oxygen donates electrons and acts as a plus some group, donating group. But when oxygen is connected like this, means in between carbocation and oxygen, if any other atom is present, then oxygen do not act as a plus sum, do not act as a donating group. It acts as a minus I group, withdrawing group. Very, very important point. Most of the students will get confusion. Okay, students will analyze like this. So oxygen is a minus I, here it is very close, now this is unstable. That is wrong concept. Here oxygen effect is plus sum, donating power, donating nature, resonance. Okay, positive resonance. Here oxygen is having minus I effect, it shows minus I effect. Here oxygen is considered as a minus I group, here oxygen is considered as a minus I group. First one is more stable, no doubt, because resonance is present, electron transfer is taking place, right? Between B and C, which is more stable? How can we predict the stability? See, Oxygen is a minus I group. Now, minus I group should be away from the carbocation, because if minus I group is closer to the carbocation, it withdraw electrons from the carbocation and makes it more unstable. So minus I group should be away always from the carbocation. Let us give the numbering. First, second, third position. Here minus I group is in third position, right? Here 1, 2, 3, 4. Minus I group is in fourth position. Fourth position. Okay, this is stable carbocation. Why? Between these two I am saying, because minus I is away. Minus I is away. This is unstable. Why? Because minus I is closer. So what is overall stability order? A greater than, C greater than B. B is least stable. Why B is least stable? In B, minus I is closer to carbocation. Okay, got it? Right. I am checking whether video is coming or not. Okay, next example. Example 3. Which is stable. See, in all options resonance is present. In all options resonance is present. Then how to predict the stability order? Here carbocation is directly connected to oxygen. Here carbocation is directly connected to nitrogen. Here carbocation is directly connected to double bond. So here also resonance is present. Shifting of pi electrons, also called as resonance. Shifting of non-bonding electrons. Shifting takes place when positive charge is directly connected to any atom with at least one lone pair. Okay, resonance is present, resonance is present, resonance is present. But which is more stable? See, in the last video I given the plus-sum order, donating power of some groups I given. I revised that order. Nitrogen is having a more plus-sum effect than oxygen, and oxygen is having more plus-sum effect than double bond. Okay, remember this. Why? What is the reason? See, which atom donates electrons easily and where stabilization takes place easily. See, if donation of electrons is easy, stabilization is more. Clear? Why nitrogen donates electrons easily? Because nitrogen is a less electronegative atom. Nitrogen is less electronegative atom, so it donates more. Less electronegativity means donation will be more. Oxygen is more electronegative atom, so their donation is less. Oxygen donating capacity is less. Stabilization is also less. Okay. So in between A and B, which is more stable? B is more stable because nitrogen is having more donating power. Clear? My question is, why double bond is coming last? Means after nitrogen and oxygen. Clear? Guess? I'll explain. See, here lone pair is donating. Lone pair or non-bonding electron donation is taking place. Non-bonding electron. Here also non-bonding. Lone pair means that is a free electron pair. It is not in any bonding, right? That is free. So we can transfer fastly, readily. Clear? But here you are transferring bonded electrons. See, this is bond. Pi bond, you are transferring pi bond. You have to break that pi bond. You have to break and you have to transfer. That is a late process. That is a late process. That's why double bond is having less plus-sum power. So what is overall stability order? B greater than, A greater than C. Very important example. Okay, right. Let us see another example. Example 4. Okay. One simple example, which is stable carbocation. First check where resonance is present. Where resonance is present. See, here carbocation is present adjacent to double bond. So resonance takes place here like this. You know what is the resonating structure for this? After shifting the pi bond, what we will get? Here we will get double bond, see. We will get double bond and this carbon will get positive charge. Here positive will be nullified. Why? This is positive and electrons are coming towards this. Electron means negative. Negative, positive neutralization. So don't write positive again here. But this carbon, see this dot carbon is losing its bond. Look at this. This extra pi bond is there now. Consider that as a marker. You are shifting the bond, removing the bond from this carbon. If carbon atom loses the bond, means loses the electron, it will get positive charge, right? Okay, finally first structure is having resonance, so it will be more stable, right? Here resonance is not present. Why? Because positive charge is not present adjacent to the carbocation. Clear? Right. Next example. Identify the stable carbocation from the given below. That is the question to you. Identify the stable carbocation from the given below. Question number 5. Same procedure. Check where resonance is present. In which resonance is present. We know structural requirement for resonance. Carbocation means positive charge should be adjacent to the atom with at least one lone pair. Where carbocation is present adjacent to the oxygen atom with lone pair. In option A, here resonance is present. Here also resonance is present. Okay, these two may be answers. Why? Because here resonance is not present. Here also resonance is not present. So these two are less stable. Our question is between these two which is stable. Once check the degree. Here resonance is present. Here also resonance is present. Both are having resonance. So resonance is cancelled. But look at the degree. Look at this degree. Here this carbocation is surrounded by how many bonds? 3 bonds. So this is 3 degree carbocation. Here carbocation, it is surrounded by how many bonds? This side 1 bond and this side 1 bond. 2 degree carbocation. In inductive effect I given. Okay, how to predict the stability based on the degree? 3 degree carbocation is more stable than 2 degree. 3 degree more stable than 2 degree. 2 degree more stable than 1 degree. Right? So which is stable? A is stable. Here resonance is present, here also resonance is present, but this is 3 degree carbocation, right? Okay. Next, stability of benzyl carbocations. Subtopic, stability of benzyl carbocations. First of all, look at this structure of benzyl carbocation. Yeah, video is coming. Stability of benzyl carbocations. This is benzyl carbocation, CH2 positive. Benzyl carbocation. We are going to discuss stability of benzyl carbocations. Plus M groups increase stability. Plus M increase stability of benzyl carbocations. Minus M groups decrease stability of benzyl carbocations. Okay, clear? You know what are plus M and what are minus M groups? Here I am writing some plus M groups. NH2OH, NHR, OR. Okay, some minus M groups. NO2 is a minus M group. Cyanide, aldehyde, all these are minus M. Carboxylic acids, all these are minus M groups. And one important point I wanted to tell you, okay, plus M group, minus M group do not works in meta position. Both the groups do not works in meta position. This is very important statement, useful to predict the stability of benzyl carbocations. Do not works in meta position. I'll tell you by taking one example. Okay, first of all, remember this statement. Plus M and minus M do not works in meta position. Do not works in meta position. Okay, I'll tell you. Now, first example. Benzyl carbocation. Benzyl carbocation. Benzyl carbocation. Its name is benzyl carbocation, right? What is the difference among these three? No difference, because all are same only, right? Now what I am doing, look at this. I am attaching NO2 and I am attaching OH, right? Substituted benzyl carbocations, right? Once look at this plus some OH is a plus some group. Now we should write the effects first of all. Very important point. You have to write all the effects. Okay, OH is having which effect? Plus some, give tick mark. I given at the beginning of the class, every plus M group also has which effect? Minus I effect. Write the effect minus I, give tick mark. OH is having two types of effects, plus M effect, donating power, as well as some withdrawing power also, minus I effect. So while predicting the stability of benzyl carbocations, you have to write all the effects. Right? Okay. Coming to NO2. NO2 comes under which group? Minus M group. So write minus M, give tick mark, minus M effect is present. Minus M effect as well as minus I also. Every plus M group also having plus M, minus M. Every minus M group also having minus M, minus I. Minus I is common. Minus I is common. Right? Okay. Right. Let us write the stability. OH is a plus M group. Plus M groups increase the stability. So C is more stable. C is more stable. Between these two, which is stable? A is stable because A is neutral. It is not connected to plus M. It is not connected to minus M. Right. So A is more stable. C greater than A. Why B is least stable? Why B is least stable? Because in B, NO2 group is, minus M group is present, withdrawing group is present. It destabilizes the carbocation. Okay, right. Next example. Between these two, which is more stable carbocation? More stable benzyl carbocation. Very easy. First, look at this. Up to this structure is same, na? Means this part. This is benzyl part. Benzyl part. Right? Very easy. Here, what is the degree of this carbocation? What is the degree? See, here resonance is present. Here also resonance is present. But what about the degree? Degree is 2 degrees, secondary. Degree is 1. So which carbocation is more stable? 2 degree carbocation is more stable. You know order 3 degree, 2 degree, 1 degree, right? Benzyl carbocations only, but based on the degree we are predicting, not based on the plus and minus M groups, because I didn't give any plus and minus M. This question depends on the degree, right? Again, let us take one example based on that, plus and minus M effects. Which is stable carbocation. First of all, write the effects. NH2 comes under which category? Plus M. Plus M. Every plus M group also has minus I power. Plus M minus I. NO2 comes under which category? Minus M. minus m and minus I. Every minus m group also has a minus I effect. OH comes under which category? Plus m. Every plus m group also has which effect? Minus I. Okay, plus m minus. Right. See, we can eliminate second option. Why? Because NO2 is a minus m. Right, ABC. We can eliminate option B. Why? Because NO2 is a minus m. Minus m groups decrease the stability. So B is least stable. So with B there is no problem for us. Problem is with A and B only. Here plus m is present, here also plus m is present. Here minus I, here minus I, everything is equal. Then we will go with the donating power, which is having more donating power. I given the order now. NH2 donating power is more than OH. OH donating power is more than double bond. I given already this. So which is having more donating power? NH2. So A greater than C, C greater than B. B is least because NO2 group is present, withdrawing group is present. Right. Okay. Example 4. This is a different example. Look at this carefully. I given one statement, plus m minus m groups do not works in meta position. Plus m minus m groups do not works in meta position. This is very important example. A, B and C. Okay. First of all, write the effects. OH is which group? Plus m. So can I write plus m here? Don't write. OH is in which position with respect to carbocation? See, what are these two positions? Meta positions. When donating group is present in meta position, OH is donating group, plus m group. Present in meta, particularly meta position, its plus m effect do not works. Cut this. Plus m effect do not works. So don't take its plus m effect. Why? Because OH is in meta. Very, very important. Remember, before that I given when plus m or minus m present in the meta position, they do not works. Okay. But minus I, OH minus I effect will work because inductive effect is a distance based effect. Okay, it will work. It will work in ortho position, meta position, para position. Clear? So minus I we can write. Minus I we can write. Very, very important example. Right? Coming to second one. Now you tell me, same OH group only present in which position? Para position. Para position. Now you can write plus m is present. Tick mark. Because it is in para. So donation is there, plus m is there. Minus I common. Minus I common. And C is neutral. This is neutral. Neutral. So arrange these three in the stability order, increasing or decreasing order of stability. First, select more stable carbocation, which is having plus m group, plus m effect. B. Where plus m is there, now plus m groups increase the stability. So B is more stable. B greater than. Problem is with 1 and C. Between 1 and C, which is stable? See, this is neutral. There is no minus I, minus m, plus I. But see, here minus I is there. Plus m is not present because OH is in the meta position. We do not consider. But it is having minus I power. You tell me what minus I groups will do? They increase or decrease the stability? They decrease the stability. So this is less stable compared to C. So B after which will come? C. A is least. Okay? Any doubt in this? Very, very important example. Right? Okay. I'll give you overall stability order of carbocations. You practice this overall stability of carbocations. Okay? After that we will go with another stability order. Overall stability of carbocations. Right? Very, very important questions are coming directly on this overall stability orders. Overall stability order. Overall stability order of carbocations. Methyl carbocation is less stable carbocation than ethyl carbocation. This is allyl carbocation. Remember, names also important. Allyl carbocation. Allyl carbocation. Allyl carbocation. Benzyl carbocation. Very, very, very important. Useful for the second year also. Benzyl carbocation. Benzyl carbocation. Tertiary butyl carbocation. Tertiary butyl carbocation. This is tertiary butyl. T stands for tertiary. Tertiary butyl carbocation. Tertiary butyl carbocation. Look at this, all of you. This is actually allyl. Allyl means sp3 carbon connected to sp2, that is allyl group. We will discuss that later. This is allyl. See, based on this I am drawing another one. Here 2 hydrogens I have, so I am removing one hydrogen and placing methyl group. Here 2 hydrogens are there, na? Remove one hydrogen and place methyl. This is primary allyl. From primary allyl we are removing hydrogen, so this is secondary allyl. Secondary allyl. So secondary allyl is more stable than this. This is more stable than this. This is more stable than this. Clear? Right. Right. Similarly, take benzyl, remove hydrogen and put methyl. This is primary benzyl. We can write secondary benzyl. When we will get secondary benzyl, remove hydrogen and place methyl group in R group. Methyl or any R group, alkyl group. Secondary benzyl. So secondary benzyl is more stable compared to remaining all. Secondary benzyl. Okay. Compare all these structures, which is more stable? Secondary benzyl. Right. Next. When carbocation is surrounded by 3 benzene rings, it will be more stable because more resonance is present. If more is the number of rings, more will be the stability. Right? Or we can represent this structure like this also. C positive, pH, don't get confusion. pH means phenyl ring, benzene ring. This is more stable. Compared to this, this is the more stable. Okay. See, continuation. Tropylium carbocation. Name is very, very important. This is called tropylium carbocation. Tropylium carbocation. Name is important. Tropylium carbocation is more stable than this also, even because of aromaticity. In this, aromaticity is present. Tropylium carbocation is more stable carbocation than this also. And the Don finally lost. Highest stabilized carbocation, tricyclopropyl methyl carbocation, king of the carbocations. Tricyclopropyl methyl carbocation. Tricyclopropyl, sorry, cyclopropyl. How many cyclopropyl rings are there? 3. So tricyclopropyl methyl carbocation. If one carbon is present, we use meth, na word, root word, meth, eth. One carbon is there, so methyl carbocation. Don. Highest stabilized carbocation is tricyclopropyl methyl carbocation. Learn this overall stability order. Okay, we'll continue later. Okay, thank you.